that's omega squared, times R2 squared C2 squared. Right? So you can put the values and find what the magnitude is. Whatever this magnitude is, you multiply it by the magnitude of input voltage, which is 10, and this goes here. How about the phase of output? Can you guess what the phase it's going to be? It's going to be the phase of input plus phase of H j omega. Okay, so what is our phase of input? It's 30 degrees or pi over 6. Right? What is the phase of our transfer function? Minus 90 degrees. I did this in radian, so I have to do this one in radian too. So it would be minus pi over 2 minus tangent inverse of omega R2 C2. Omega is 2 pi 60 times R2 C2. So again, you put the values here, you find the phase. You just have to make sure that you either stick with radian or stick with degree. You can't mix them, right? And whatever it is, it's gonna go here as the phase. So this is how you can solve this problem. I'm just gonna do one more example for Bode plot to make it clear for you guys. Okay, and for this course, we only focus on the poles that happen on the real axis. So either here, 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 here. Poles and zeros that are on real axis. We don't do the complex poles that might be happening here, here, here. So that's gonna be a little bit more complicated, which we're gonna cover in your next course, but not here. So let's assume that we have something like this divided by 1 plus j omega 1000, 1 plus j omega 100. Okay, actually let's make another 0 here, j omega, and let's make one of these actually squared. Okay, so the first step is to find the zeros and poles. How many zeros do we have and how many poles do we have? Okay, can you guys tell me? Oops, sorry again. I think this is not perfect, so I'm just gonna hold it. Okay, and maybe I should have a more like that. Okay, so how many zeros do we have? We have 1 0 at j omega equal to 0, 1 0 at 0.1, and 1 0 at 1. Okay, how many poles do we have? We have 1 at 100 and 1 at 1000. Okay, but the pole that we have on 1000, we actually have 2 poles at 1000. So this is a double pole. Okay, so if I want to draw our poles and zeros here, this is what we have. We have here at 0 we have a 0, sorry. At 0.1 we have a 0, at 1 we have a 0, and we have, this is not scaled properly, but this is, sorry, 3 zeros here and a pole at 100 and 2 poles at 1000. Okay, so now let's do the magnitude Bode plot. Okay. Okay, so what I'm gonna do here, first of all, so I need to go up to 1000. So like, let's make this one 10,000, 10 to power 5, or 10 to power 4, sorry. Or actually, let's go to 10 to power 5. This is 10 to power 4. This is 10 to power 3, 10 to power 2, 10 to power 1, 10 to power 0, 10 to power -1, and so that's what I was saying, that like we don't actually have an origin for the vertical axis here, for the horizontal axis here. You can go as small as you want depending on your problem. So here, like, I'm just gonna go to 10 to power -2. Okay, so first of all, let's say at omega equal to 0, what is our transfer function's value? Because of this 0, it's going to be 0, right? So we have a 0 in the origin, right? The impact of this 0, as I mentioned in the previous section, for the previous one, it's just going to be increase in the magnitude with the slope of 20 dB per decade, but it's going to go through j omega equal to 1. Why am I? Yeah, this is 10 to power 0. 10 to power 0 is 1. Okay. Now, what's the next thing that we have? The next thing that we have is a pole that we have at, sorry, a 0 that we have at omega equal to 0.1, which is here, right? 0.1. So, and this one, again, we have a 0. So this is going to cause, I'm just going to do all the poles with red. So what's the impact of the 0 on the magnitude Bode plot? It's going to be, again, raise with the slope of 20 dB per decade. Okay? And we have another 0 at omega equal to 1, okay? At omega equal to 1, we have another 0, right? So this happens to be exactly at this point that we have. So in this case, I have to do it. So we're gonna have another 0. This goes up to here, but